This video is going to cover concentric design of columns. What that means is that the load is concentric, meaning the load is at the center of the cross-section. So the only thing that's actually going on now if we have concentric loading is that we only have axial stress, which is again P over A. That's kind of nice for us. In order to do column design, we do have to have a slenderness ratio. And slenderness ratio is KL over R, KL being the same effective length that we had before. So K is that column coefficient about the end supports, and L is the length between supports. And R, new thing here, is the radius of gyration, and that is the square root of the moment of inertia divided by the area. Now you might be thinking, wait a minute, don't we have two different moments of inertia? And you'd be right, which also gives us two radius of gyration. Technically, you're supposed to check both. Now, I will say that the smaller slenderness ratio is the one that's not really going to control. And by that, I guess a better way to say it would be the larger you are here, the more slender you are, the more likely you are going to control the design. Because if you have a short, stocky column, the column is not really likely to buckle. So it's going to actually hit yield stress. However, if you have a really long column, right, higher slenderness ratio here, higher slenderness. If you have a really long column, then that long column is more likely to buckle before it ever hits the yielding stress, which means obviously it's going to buckle first at a lower load. Hence why the more slender you are, the higher this ratio is, the one that's going to control. The more likely you are to buckle ahead of time. So technically with design of columns, we have three different types of columns. We have steel columns, and they have two equations, and they're not very fun equations. The first one's not quite so bad. The second one is kind of bad. There's technically a little break here. So we have two different things. This is for a long column, and this is for a short column. How do you know what the difference is between a short and a long column? That's where this guy comes in. He is our little critical here for between short and long. So, and he is simply square root of 2 pi squared times E divided by sigma y. These values, technically, they can be in KSI and KSI. E is the modulus of elasticity, sigma y is the yield stress. So he's just going to be a flat line number dependent on the material properties, because it makes sense, right? A short column is going to yield before it's going to buckle. A long column's obviously going to buckle. So if you're long enough to get past yielding, then there you go. So if you're long, you get the nice, pretty equation. And if you're short, you get the world's nastiest equation, which again really actually has two variables if you think about it. There's KL over R, who is this one, who appears here and appears here. And then there's KL over RC, who's there, and there. So it would actually look a lot prettier if you changed those into like an alpha and a beta, and then it wouldn't look quite so terrible. But anyway, he is not exactly beautiful. So for steel, two different equations. And for aluminum, we have three equations. And again, it's kind of the same thing. Here it's we have a KL over R, and we're checking it. Are we in the 0 to 12? Are we in the 12 to 55? Or are we in the 55 plus range? And you can see we have different equations for sigma allow based on that, all with KL over R except for the first one, who's just a flat plateau. And for wood, again, we have three equations. This time, though, KL over D, which you might think looks really weird. The only difference is that D is the smallest cross-section dimension. Yeah, so actually easier to solve because it's, not anything to do with radius of gyration. So that's kind of nice. Again, starts off as a plateau. Then we have the 11 to 26 range. And then we have the 26 to 50 range. And you might be thinking, wait a minute, what if my KL over D is greater than 50? Well, sweetie, you can't use it. Same thing with way over here with steel. There is technically an upper limit, and that's 200. And if you exceed that, well, you can't have a column that slender. Hate to tell you that. So how do you actually do column design? Technically, there's three different types of column design we can do. We can either design for the maximum load, we can design for the length, or we can design for the cross-section size. Maximum load isn't really a design question, it's really more of an analysis question. So if you're doing maximum load, all you have to do is figure out what your KL over R value is and pick your correct equation and solve for the allowable, and then set your allowable equal to your axial, right? Solve for P. Quite simple if given some actual sizes of a column. Very, very easy. If you're not given a length, well, then you have to actually kind of guess and check. You know an axial. You're going to set it equal to an allowable to solve for a KL over R, and then you're going to check to make sure that it's actually within your range. And if it is, cool, you can use that one, but then also don't forget to check the other guy. Solve for a new KL over R, make sure he's within the range, and then whoever's the longer column is obviously going to control. So that's not really that bad. What gets really terrible, though, is when you know L, you know P, but you don't know R. Yes, if it's actually a circle, he's really simple, because again, moment of inertia is in terms of radius, areas in terms of radius. So technically, yeah, you only have one little variable. He's not a very pretty one, but again, it's the same thing as L. That's not hard. The hard part comes when it's essentially a W shape, where you have moment of inertia, you have area, and those are very radically different things. Again, if you're talking like a rectangle shape, it's not really that hard. You'll have an A, you'll have like a, I don't know, a 1.5 A. And again, you can calculate the area of the shape and the moment of inertia in terms of one letter and you'll be fine. But a W shape, that's a whole different story. So let's do that. Let's actually, given a load of 40 kips, given the fact that it's a pin-pinned steel column made of A992 steel of length of 14 feet, we want to find the lightest W shape. Now, technically, to be able to find the lightest W shape, you technically have to look at the entire list of W shapes, which is a bit much. So anytime that you might notice when you're finding the lightest W shape, they usually give you an option. Like they might say something like, find the lightest W14 shape, or pick from a list of these 6 which one's actually the lightest one that works. So kind of giving you a little bit of an idea of where to look. In reality, this is not how you would design for steel columns. You take your actual load, you go look it up in a table, and it will tell you what the maximum load is for that column. And you just go to the lightest one. Ta-da, it's actually pretty simple. But we don't have that. Not in this class, no. So now we're actually going to solve for this. So again, where do we really start from? Well, we have a sigma actual, at least a little bit. That's P divided by A. But again, I don't really know what A is, so it's not actually really cool, but we can go ahead and write it out just a little bit here. We can say that P is 40 kips and A, well, I don't actually know A. Okay, so that's as far as I can get with this dude. I'm gonna just underline him. Okay, that's as far as he goes. And again, if I want to find one of my values, L or R, again, I said that we have to set our actual equal to our allowable. But again, if you don't actually know the size of the shape, how do you know which one to use? So we got to technically guess and check both. But again, the slender the column, the more slender the column, the more likely it is going to control, right? So the longer it is, that's going to control. So let's shoot for a long column. That would be wonderful, actually. Let's shoot for a long column. So for a long column, we're going to try the long, and we're going to pray. So for a long column, we have our sigma allowable is equal to 12 pi squared E over 23 times KL over R squared. Okay, so pretty much we can plug in a lot of information about this, actually. We have E. Maybe you don't necessarily know it off the top of your head, but E is 29,000 KSI for steel. So cool. So we actually do know that. We have K. K here, you might not think we were given it, but we know that it's pin-pin. So if it's pin-pin, then we know K. K would be 1. L is straight given to us. right? So there's L, there's L, have that, cool. The only thing we don't know is R, the radius of gyration. So, okay, we can solve for this. So let's start. We have 12 times pi squared times 29,000 KSI divided by 23 times K, which we said was 1 because it's pinned, L, who is 14 feet. But let me remind you that radius of gyration, if you're looking at the units for this guy way up at the top here, radius of gyration is the square root of inches to the fourth over inches squared, which means he's in inches. So in order to keep a ratio as a unitless number, kind of have to make sure that L effective is in inches, just like we did before. So, all right, 12 inches here and 1 foot divided by R. Well, we don't know R, so that's cool, squared. But we do have a lot of numbers. And since we're dividing by another division, I'm technically multiplying by R squared. So I'm going to get a really big number for sigma allow here. Well, big on the top, big on the bottom, magically actually shrinks it down to something not quite so big. And that's 5.29 R squared. So again, if you do the big number on the top, this is technically 3434622. So 3,434,622 over 649,152 divided by R squared. So again, the fact that we're dividing by R squared means we're technically multiplying by him. So, and then if you just shrink down this dude, you'll get 5.29. Cool, so how did this help me? Well, again, don't forget, we can set sigma allow and sigma actual equal to each other. Is this really helping though? Let's check it out. We have 5.29 R squared is equal to 40 divided by A. Okay, that's not really helping much. But what do we know about R? R is the square root of I over A. And if we square this, then technically our square root and our square is going to cancel. So R squared is equal to I divided by A. Can that help us? Sure. So over here we're going to have 5.29 times I divided by A is equal to 40 divided by A. Now A's cancel. Hell yeah. So what I'm going to get now is something in terms of moment of inertia. So 40 divided by 5.29 is a 7.56 inches to the fourth. What do I do with this information? Well, now I'm going to go to my steel charts. And in my steel charts, what I'm going to look for is I'm going to look for my moments of inertia. All right, so in my steel charts, I'm looking at IX and IY. However, remember that if our ends are the same, if our end supports are the same, so here I'm pin in both directions, then yes, I get to use the smaller value of I. If it's not the same, this problem gets even freaking worse. Conveniently, it is pin, so I'm going to be looking for the smaller I value. So that's technically going to be on IY for all of them. Well, where do you start? The smallest W shape and just go up and just write a whole list? Well, conveniently for this problem, let's say we're going to make a list of a few choices. We have a W6 by 12. We have a W10 by 12. We have a W12 by 14. We have a W6 by 15. We have a W8 by 15. And we have a W10 by 15. These are going to be our 6 options. Now, as you can see, I've organized them from lightest down to heaviest. So obviously, I'm hoping to start with the smallest one and work my way up. So I'm going to go to my steel charts, and I'm going to check out what my moments of inertia are for each of these members. And for the W6 by 12, we have 22.1 and 2.99. For the W10 by 12, we have 53.8 and 2.18. For W12 by 14, I have 88.6 and 2.36. For W6 by 15, we have 29.1 and 9.32. For an 8 by 15, we have 48.0 and 3.14. For W10 by 15, we have 68.9 and 2.89. So, now what? Technically what I'm doing is I'm looking in this column for a number who is greater than 7.56, right? Because I have to at least be that big. So if I'm going through, well, he's not bigger, he's not bigger, he's not bigger, he's not bigger, he's not bigger. This guy's the only guy that works. Is that the answer? Hold up, let's check. In order to be able to use our long equation, which we said we were trying, we're hoping here, in order to use that, we had a little condition. We said that KL over R has to be greater than KL over RC. Okay, what was KL over RC again? Way back up here, we had an equation for it. The square root of 2 pi squared times E divided by sigma y. What does that actually give us? Let's go check. So again, we said square root of 2 pi squared times E. E was 29,000 KSI. And you might be wondering, what's sigma yield? Technically, at some point in your life, you're probably going to remember this. If not, it's okay. But A992 has a yield stress of 50 KSI. That's its kind of magic. If you had A36, his yield stress is 36 KSI. Both of them are steel, both of them have the same E. So, ta-da, you could also look that up from a table. But we have a yield stress of 50 KSI. So, divided by 50. What do we get for this guy? 107. Is our KL over R greater than 107? How do I know? Well, back up here in the table, there's also going to be Rx and Ry. So now that you've selected your dude, let's go figure out Rx and Ry. Well, technically, who's going to control? Again, the more slender guy is going to control. More slender means that this has to be a big number. To have a big number, that means that this guy has to be smaller. Which does also mean that that's going to be Ry for us. So our Ry value that we're going to read for a W6 by 15 is going to be 1.45. So let's check it. What's KL over R? Again, K for a pin. We said a pin was 1. We said the length of the column was 14 feet. We said we need to turn that to inches, so 12 inches in a foot, divided by R, who we just found, 1.45 inches. And what we get for KL over R is 115.9. Is that greater than 107? Yes. So therefore, we have satisfied that condition. It is a long column, and again, it satisfied our moment of inertia. So, yep, the answer that we're going to choose is a W6 by 15. This is, again, the worst thing possible that you can do in terms of design of columns.